Hey everyone, welcome back to the channel. Today, we're diving into one of those absolute baseline topics that every civil engineer, structural designer, or student needs to master. Reinforced concrete slabs, specifically focusing on the critical provisions from IS 456 to 2000. If you look at the textbook definition, a slab is a flat, two-dimensional planar structural element where the thickness is tiny compared to its length and width. But in simple words, its main job is straightforward. Give us a solid, flat surface to walk on, or act as a protective roof over our heads while transferring all that weight safely by bending. You see them literally everywhere, in floor systems, roofs, walls, and bridge decks. Slabs can be classified in a bunch of different ways. You can group them by shape, like square, rectangular, or circular. You can look at how they are supported, whether they rest on walls, monolithic beams, or directly on columns, which we call flat slabs. But when it comes to everyday practical engineering and structural design, the most critical way we look at them is based on their spanning directions. This splits them into two major groups, one-way slabs and two-way slabs. Let's understand how a slab actually responds when a heavy load pushes down on it. A one-way slab happens when it's supported strictly on two opposite parallel edges. But here is a vital rule of thumb from the code. Even if a slab is supported on all four sides, if the longer span, L_y, divided by the shorter span, L_x, is greater than 2, it still structurally acts as a one-way slab. It creates what we call a cylindrical deflected surface. This means it essentially bends in just one direction. Because it only bends across that short gap, we place our main structural tension steel bars strictly along that shorter spanning direction to fight the bending. On the flip side, we have two-way slabs. This is when our slab is supported on all four edges, and the ratio of the long span to the short span, L_y, L_x, is less than or equal to 2. Instead of a cylinder, it bends in two orthogonal directions at the exact same time, deflecting in the shape of a dish or a saucer. Because it bends this way, the corners of the slab naturally want to curl up and lift straight into the air under weight. If those corners are completely free to lift, we call it a simply supported two-way slab. But if the slab is cast monolithically together with the supporting concrete beams, those corners are physically locked down and restrained from lifting. These are called restrained slabs. Because those corners are forced to stay down, heavy internal twisting forces, or torsion, develop right at the corners, which completely changes our design approach. Before we can even think about calculating steel areas, we have to establish our physical geometry and figure out our design loads. First up is the effective span, covered under clause 22.2 of IS 456. When you look at a room, you see the clear space between the walls. That's your clear span. But structurally, the code states that the design effective span length must be the lesser of two values. Either the clear span plus the effective depth, d, of the slab, or the center-to-center distance between the supports. Next, how thick should our slab be? The initial trial depth depends on your bending moment and your deflection criteria under clause 23.2.1. If you have a short span under 3.5 meters with light loading, the code gives us a baseline span to effective depth ratio, LD. For a simply supported slab using mild steel, Fe 250, the ratio is 35. For a continuous slab, it's 40. But because almost everyone uses high-strength bars like Fe 415 or Fe 500 today, those limits must be multiplied by 0.8, dropping them to 28 for simply supported and 32 for continuous slabs. If you want a quick engineering rule of thumb, you can assume your initial trial depth based on these ranges. For a one-way slab, your depth will usually be around 1/22 to 1/28 of your span. For a two-way simply supported slab, aim for 1/20 to 1/30, and for a restrained two-way slab, look at 1/30 to 1/32. Once that depth is locked in, you calculate your loads per square meter. You take your dead load, which is just the total slab thickness multiplied by the unit weight of concrete, which is 25 kilonewton per meter cubed. Then you add your floor finish, typically 1 to 2 kilonewton per meter squared, and your design live load. Alright guys, let's talk about the absolute law book rules. The detailing requirements as per is 456 to 2000. You cannot just throw steel bars wherever you feel like it. The code sets strict boundaries to prevent rust, shifting, and cracking. First is nominal cover, clause 26.4. For normal, mild environmental exposure, you need a minimum of 20 millimeters of clean concrete protecting your steel. However, the code gives us a great little shortcut. If your main reinforcing bars are 12 millimeters or smaller in diameter, you are allowed to reduce that cover by 5 millimeters, meaning a 15 millimeters clear cover is perfectly safe and compliant. Second is minimum reinforcement, clause linked to 26.5.2.1. Concrete shrinks and expands with temperature changes, which causes cracking. To control this, we must provide a baseline mesh of steel even if the loads are tiny. If you are using ordinary mild steel, Fe 250, you must provide a minimum steel area of 0.15% of the total gross cross-sectional area. If you are using high-strength steel like Fe 415 or Fe 500, that minimum drops to 0.12%. Third is spacing of bars, clause 26.5.3. Your bars cannot be clustered together or spread too far apart. For your main tension steel, the maximum center-to-center spacing cannot exceed 3 times the effective depth, 3D, or 300 millimeters, whichever is smaller. For your secondary or distribution steel, the limit is wider, capped at 5 times the effective depth, 5D, or 450 millimeters. Fourth is the maximum diameter of a bar, clause linked to 26.5.2.2. To make sure the slab stays flexible and properly balanced, the diameter of any reinforcing bar can never exceed 1/8 d8 of the total thickness of the slab. So if your slab is 120 millimeters thick, your maximum bar size is 15 millimeters, meaning a 12 millimeters bar fits perfectly, but you cannot use a massive 16 millimeters bar. Now let's tackle the masterclass topic, two-way restrained slabs. When a slab is cast monolithically with beams, we don't treat the entire surface the same way. The code tells us to mentally divide the slab into strips in both directions. We have middle strips, which take up the central 3/4 of the span, and edge strips on the outer boundaries. The maximum calculated bending moments from our code tables apply only to this middle strip. In the edge strips, you only need to lay down your minimum baseline temperature reinforcement. Because the edges are locked into the beams, negative bending moments build up directly over the supports. This means we have to calculate 4 separate moments, positive and negative for the short span, and positive and negative for the long span. Now, remember those curling corners we discussed earlier. Because the corners are held down, intense twisting forces develop. To stop the concrete from tearing apart at the corners, clause Appendix D mandates that you must provide a dedicated torsion reinforcement grid at both the top and the bottom faces of the slab. This grid must have an area equal to 3/4 or 75% of the maximum regular midspan steel area, A_STX. And this grid has to extend inward from the edges by a distance of exactly 1/5 or L_X5 of your shorter span length. If you follow these strip layouts and corner rules, your two-way slab will be incredibly safe, structurally sound, and code compliant. To wrap it all up, check your aspect ratio first, choose your trial depth, pull your bending coefficients from the code tables, calculate your steel areas, and always run your final detailing checks. If you want to see a full numerical math example using these exact formulas, make sure to hit that subscribe button, drop a comment down below, and check out the next video in this series. Thanks for watching, study hard, and I'll see you in the next lecture.